It's an honor to be here, virtually, to accept this Lasting Impact Award on behalf of my collaborators, Julia Schwarz and Chris Harrison. We're thrilled that our finger angle project was chosen for this award, and in this short talk, I hope to give you a bit of behind the scenes on the project itself and the impact it's had on the community. So, conventional touchscreens, as we all know, back in 2015 and still now, mostly in 2024, report only the XY positions of touches. Now, while this has been enough for a range of multi-touch interactions, it captures only a small fraction of what the human hands are actually capable of. So in 2012, Chris, Julia, and I founded a company called Xiao with the broad goal of commercializing rich touch solutions, that is, touch input that goes beyond just finger position. We started with TapSense, a system for distinguishing taps from different finger parts like nail and knuckle taps, that had been published by Chris and Julia the previous year at WIS. Now, our original prototype of TapSense used a piezoelectric sensor to detect the different vibrational characteristics of different taps, but for commercialization we were looking for more sources of data that wouldn't require installing a brand new sensor. So in 2013, while I was looking at Xiao, we decided to investigate a new feature released with the Samsung S4 called AirView. With AirView, a user can hover their finger over the screen to activate different functions, such as a magnifier here, a very unique and somewhat rare capability on smartphones. And we were curious just to know how it was detecting hover input on a normal touchscreen. Now, what we discovered entirely by accident was that Samsung had actually exposed an internal touchscreen debugging feature on the S4, probably to debug AirView. Now, this debugging feature allowed us to read the raw capacitance data from the touchscreen controller on a rooted phone, and this capacitance data consists of one reading for each cell on the capacitive grid. We can render that as the so-called capacitive image. Now, this is pretty low resolution. For this phone, it's just 16 by 28 pixels, but as you can see in this picture here, it already gives you a lot more information than just an XY coordinate. Now, as far as we understand it, this feature is an internal undocumented function known as function 54 developed by Synaptics for their touchscreen controller, and it wasn't ever meant to be exposed. But Samsung had specifically modified their kernel driver, their Linux kernel driver, to expose this function to user space. And now when we first tried to read this capacitive image repeatedly, we could only get it at a pretty low frequency, about 6 frames a second, and the driver would actually crash occasionally, rendering the whole touchscreen unusable until you rebooted the phone. So I rolled up my sleeves and learned a little bit about kernel, how to build and modify the Linux kernel. And after some trial and error, I found that literally just overclocking the serial connection to the touchscreen driver worked just fine. So here what we can see is the actual patch that we use to overclock the serial driver. I just bumped the serial driver's frequency, the I2C frequency, up from 384 kilohertz up to 1.6 megahertz over a 4x increase, and somehow the touchscreen still works just fine. With a couple more tweaks to fix the driver instability, we're actually up to a buttery smooth 25 frames a second, giving us a capacitive video. So this is also a really fun way for me to use some of the kind of the security hacking that I do in my hobby and apply that to an HCI problem. So we built a little app to visualize the capacitive image, and you can see that right here on the right. And after playing with it for a bit, we figured out we could probably sense the angle of the finger. You can actually see me playing with that in the video here. And that would be really useful for interaction. Past work in this area, like angle pose and point pose, had shown how to do this with custom capacitive sensor arrays or with vision sensors like depth cameras, but doing it with an off-the-shelf touchscreen phone felt both a lot cooler and a lot more practical for real-world deployment. And to just up the cool factor a little bit more, well, we've been playing with smartwatches too, and we found we could actually hack the LG G Watch, this little smartphone here, smartwatch here, to get its cap image too. And we did this by just deleting its capacitive, its touchscreen driver entirely and replacing it with the Samsung touchscreen driver, and somehow that all works. And this gives us a tiny 8x8 pixel capacitive image running at 60 frames a second. Now, to determine the finger angle from the raw capacitive image, we first processed it to extract feature descriptors. We located that touch blob via a flood fill algorithm. Then we derived 7 weighted capacitive images by applying different functions to the capacitive read-ins. And finally, we derived 6 statistical descriptors by fitting an ellipsoid to each one of those images. For the actual model, we actually built a pretty simple model to extract the pitch and the yaw of the finger. Pitch was determined through a Gaussian process regression model, and yaw was just determined from the ellipsoid orientation, plus a couple of corrective heuristics when the pitch angle increases. So we use the major angle when the finger is low to the screen, and the minor angle when the finger is up higher. And we didn't otherwise use any really fancy machine learning. So then we did a user study. Specifically, we set a couple limitations in the user study. We tested it using a single pre-trained live model that was trained just on data from the 3 authors, without any post-hoc algorithm updates or per-user calibration. So this way, it's really kind of representative of the real accuracy achievable in practice. For actually testing different pitch angles, just to ensure uniformity, we laser cut these little plastic wedges that we stuck underneath people's fingers that would allow us to place the fingers at specific angles. And in the end, our results showed that our mean pitch error was in the range of 10 to 15 degrees, more for the watch. It's a smaller screen with less data. With the yaw error averaging around 30 degrees error. But it's worth pointing out that the yaw error was primarily concentrated with pitch angles between about 45 to 60 degrees, because at those angles, the contact patch is nearly circular, no matter what the yaw is. And finally, Julia put together a really sweet set of demo applications to showcase the system. So here's some of those applications here. So first, because watches are really tiny, there's limited room for touch interaction. So the finger angle can be used as an extra dimension that's easy to perform even on a tiny little screen. So for example, in that first sample you saw, it can be used to adjust the volume, now to zoom in or out, or even rotate images like you see here. And here we can see that zooming again being applied to picture. On a phone, we can use the capacitive image to rotate a 3D model. So we can do 3D manipulations in all directions using the finger rotation. Or we can even play a game, controlling this little rocket ship in space. This is probably my favorite demo of them all. So that's a whirlwind tour through basically finger angle. And now I'd like to talk a bit about how this paper has had a lasting impact on the ISS community. So first, I'd like to show, first just a couple of the papers, even from our lab that we had published based on extracting and processing the capacitive images. So CapAuth, which was published actually at the same conference at ITS 2015, was a system to authenticate users based on their unique capacitive signature. And we demonstrated that we could authenticate between 20 different users with 99.6% accuracy. The next year, at ISS 2016, we published CapCam, which lets us quickly pair a phone to a larger touchscreen, and here a Microsoft Surface, to create positionally tracked cross-device interactions. When a phone is pressed to a screen, a pairing code is flashed underneath the phone's camera, enabling those devices to connect instantaneously with no prior arrangement, and then enabling these lovely positionally tracked interactions. And of course, this all works using the capacitive image. So in the case of the Microsoft Surface, I was able to dump the raw capacitive image off the Microsoft Surface's USB protocol and use that raw data to detect fingers and phones. And later, that idea of overclocking a sensor with a kernel hack would actually really come in useful in Viband, a WISP-best paper from 2016. We again used the LG G watch, since we had familiarity with it from finger angle, but this time we overclocked the inertial measurement unit, the accelerometer, with a custom driver to acquire a sensitive vibroacoustic signal, and then allowing us to implement all sorts of interactions, all with stock off-the-shelf hardware. And now I want to talk about some projects outside our own lab. So together with Holtz's body print, which was published in the same year, these papers demonstrated to the research community the value of getting the capacitive image on commodity hardware and paved the way for future work which exploits that capacitive image. Now, finger angle has been cited nearly 100 times, so I'm just going to show a couple of my favorite projects. At ISS 2017, Mayer et al. Presented a significant improvement on our original finger angle algorithm, significantly reducing both the pitch error and nearly halving the yaw error using a convolutional neural network trained on a data set of raw capacitive images. So this technique brings that finger angle technique a lot closer to being commercially viable. And kind of even more ambitiously, at WIS 2021, Ahuja and colleagues presented a system that recovered the entire hand pose from capacitive images, recovering the angle for each finger and then applying inverse kinematics to solve for the whole hand pose. So this is just some of the really cool papers that have been built on the finger angle concept and the use of those capacitive images. And so finally, I'll note that our approach of actually extracting that capacitive image from ordinary devices ended up really being useful for our startup company Kixo as well. So although we never commercialized finger angle itself, the capacitive image approach ended up in two of our products: FingerSense, which distinguishes fingers and knuckle inputs rather, which was shipped on Huawei phones and has been shipped on Huawei phones to this very day, and EarSense, which detects proximity using the touchscreen, eliminating the need for a dedicated proximity sensor, and that was shipped on Oppo devices. In total, these two projects shipped on over 200 million units worldwide by February of 2019, and that was using capacitive image analysis techniques, which were originally pioneered in finger angle. So that was a quick tour of all the cool things that came out of our work on finger angle from ISS 2015. Thanks all for listening.